Thank you. Hello, I'm Ryan. I'm here to talk about how to use probabilistic programming to get better distributions out of the generators you use for property-based testing. So first, property-based testing, or PBT, is a technique that validates a system under test against an executable specification or property. For example, if we'd like to test the list reversal function, we might want to use the property that whenever you reverse a list twice, you get back the original list. And then to test this property, we use a program which we call a random data generator, which will randomly generate samples that are inputs to our property. So here, we'd randomly generate lists. And in PBT, the effectiveness of our testing depends on the distribution of our generator. So let's look at an example. Here's a generator for Boolean lists of up to length n. In the common case, we first use the frequency combinator in order to uniformly choose between two branches, since both have weight 1. It either chooses nil or cons, and in the case where we generate a con cell, we use flip to generate a Boolean payload for our list. That's true half the time and false the other half. And now we can run our generator to get our set of samples. But immediately, we can see that this set of samples isn't very effective for random testing because almost all of the lists are empty or have only a few elements. And this is because of the weights we chose for our random generator. In particular, if you evenly choose between generating nil or cons, half of your lists will be empty. So instead, we can generate cons more often, say 3 times as often as we generate nil, and then rerun our generator, and we get a better set of samples. But we shouldn't be satisfied with this process for a few reasons. The first is that in general, it's difficult to reason how the weights of your generator affect the final distribution, especially as the generator gets more complicated. The second reason is that we were pretty ad hoc in coming to this distribution, and we'd like more principled ways to find distributions that are better at bug finding. So this problem of generator tuning is well recognized in PBT. Some of my collaborators did a study on how developers use property-based testing, where they found that choosing probabilities is a mental strain. And there's a good blog post by John Regier in which he says that the most difficult and unsatisfactory part of engineering a good random tester is setting the probabilities properly. So we've seen the problem, which is that controlling test distributions is critical but difficult. And our proposal is to instead automatically tune our generators for desirable distributions. And to do this, we view generators as probabilistic programs. And this is useful because the probabilistic programming community has developed many techniques to reason about the distributions of probabilistic programs. So we can use these techniques to tune our generators. To see what we mean when we say that generators are probabilistic programs, let's look back at our example generator. The key property of probabilistic programming is that the result of a probabilistic program, or its semantics, isn't a single sample, but rather the distribution of values that it can produce. So here, we see that our generator has a 50% chance of generating nil. And then, because we don't actually know what weights to choose for our generator, we can use symbolic weights instead. So here, we've chosen theta n and theta c for the relative probabilities of choosing nil and cons, and theta t for the probability of the flip being true. And the key part here is that this now gives us a symbolic distribution, which allows us to recast the problem of generator tuning as finding assignments to our symbolic weights that result in the most desirable distribution. So as a simple example, let's say we want to maximize the probability of generating the list false, false. Well, this probability is right here in our symbolic distribution, so we just maximize this expression, which turns out to be done by setting the values of theta n, c, and t to 1, 2, and 0. And this example actually demonstrates the workflow that results from our approach. As the input to generator tuning, we have a generator with symbolic weights, such as the bool list generator we just saw, and a probabilistic objective, such as maximizing the probability of generating false, false, or maybe more realistically, something like targeting a uniform distribution over list lengths. Then as the output of generator tuning, we get our tuned weights. We have 2 main contributions that support this approach. The first is that we actually have to implement a probabilistic programming system that allows us to learn weights. We call this system loaded dice. The second is that once we can tune, we need to know what to tune for. So we propose some generator independent objectives that allow us to find bugs faster. And in our evaluation, we find that when tuning type-derived generators, we find bugs 3 to 7 times faster. So the rest of this talk, we'll go into each of these contributions in some more detail. First, we'll talk about how we implemented loaded dice. So we'll start with a simple example that's basically as simple as possible just to fit on the slide. We'll say that our generator is if a flip with probability theta is true, we return 2, otherwise we return 3. And our objective will be to target the distribution where we always return 2. Just as a quick aside, so far we've been saying our objectives in English, but the way we really specify it is as a function from distributions to real numbers that indicate how desirable those distributions are. So as we saw before, the first step was to, for a generator, compute the symbolic distribution of the samples it can produce. So for this generator, it can generate 2 with probability theta, or 3 with probability 1 minus theta. And then what we do is we combine the symbolic distribution with our probabilistic objective in order to get a loss function, which is just an expression we can minimize in order to find the theta that optimizes our distribution, that optimizes our objective. So here, this ends up being a theta of 1, as we'd hope. There are 2 main components in this process. The first is probabilistic inference, which is the task of computing the distribution from a probabilistic program. And the second is gradient descent, which we just use to minimize the loss function. Now, in implementing this, there are 2 main scaling challenges we face. The first is that the naive method for computing the gradients of a probabilistic program requires enumerating all of its execution paths. And the solution here is that it turns out that the state-of-the-art technique for doing probabilistic program inference is differentiable, so we can use the same technique to compute gradients. This technique is knowledge compilation. We don't have time to get into the details, but the gist of it is that for every sub-expression of the probabilistic program, we use a BDD to represent its distribution in a compressed form. And then, even once we can compute gradients, we still have the problem that some of the objectives themselves that we'd like to tune for, such as entropy, which we'll discuss soon, enumerate a generator's distribution just to express. And what we do here is we create gradient estimators for these objectives that allow us to approximate their gradients by sampling without needing to compute them exactly. And the specific technique we use here ends up looking like reinforce for those of you who are familiar with it. So with these improvements, we now see how to tune generators, but we'd also like to know what to tune them for. In some cases, the user might have a specific desired distribution in mind, and we can tune for this by setting our objective to minimize the distance between the generator's distribution and the desired distribution. And we can use a standard metric for distance between distributions, such as KL divergence. But the user doesn't always have a distribution in mind, so we'd like to find properties of distributions that are useful for bug finding in general. Turns out there are already some well-recognized properties that follow this in PBT, specifically validity and diversity, but we find that when we tune for these individually, they naturally conflict. So first, validity is useful when there are property preconditions you'd like to satisfy. So for example, for this generator, or for this property, it tests that for any colored binary tree, if it's a valid red-black tree, when we insert a key and value into it, then it should still be a valid red-black tree. And the thing to notice here is that if we generate a tree that's not valid, then this property is vacuously true, so those samples wouldn't even test the insertion function. So we want to generate valid red-black trees. And we can express this as an objective straightforwardly, where we want to maximize the probability that our generator produces a valid tree. But when we do this, we find that we get trivial samples. It turns out the easiest way to generate valid red-black trees is just to generate trees of one node. And it turns out this actually makes us generate fewer unique valid red-black trees than our untuned generator. But this actually points us to the other desirable property, which is that we'd like some notion of diversity among our samples. The intuition here being that diverse samples will exercise more execution paths in your system under test. However, when we tune for diversity, which we do so using a standard metric for the diversity of a distribution, entropy, we find that this is degenerate in a different way, that it incentivizes large and valid samples. Larger trees are easier to make diverse, but harder to make valid. So again, we find that when we tune a generator for this objective, we actually end up doing worse than our untuned generator. And these two objectives are in genuine conflict. We can't just take a weighted combination of them. So instead what we do is we propose a new objective that we call specification entropy, which values diversity, but only within the valid subspace of samples. And as we'd hope, when we tune for it, we find many more unique valid red-black trees than the other objectives we considered. As an example of using this objective, we took a generator for terms of the simply typed lambda calculus and tuned it so that it would make samples of diverse types. So this chart shows the distribution of the types of the terms we generate throughout tuning. At the beginning, most of the terms we generate are not well typed or of type bool, but by the end, there's a wide representation of types, none of which are overrepresented. Of course, this distribution looks good for tuning, but what we really care about in property-based testing is whether or not we're actually finding bugs. So for this, we performed an evaluation on ETNA, which is a set of PBT benchmarks. It contains a standard set of pre-placed bugs and properties, and we used it to determine the bug finding speed before and after tuning. And we found that when tuning type-based generators for specification entropy, we found bugs 3 to 7 times faster. So to conclude, we present an approach to automatically tune generators via declaratively specified distributions. Thanks for your attention.
Thank you for the talk. We have time for a few questions.
John Hughes, Chalmers.
Yeah.
So one interesting kind of test case is that collisions of values may be interesting. For example, when we test registries, you may want to generate the same name repeatedly. So can you specify that kind of property in your distributions, that you want some correlations between generated values?
Yeah, so I guess I could imagine you have a generator that produces 2 values, and then on that you can specify any property of the distribution. I'm not sure exactly how you'd want to incentivize 2 values to be the same, but...
No, so I'm imagining that you generate a sequence of operations, each of which manipulates a name in the registry, and then you're going to be generating the names separately, but it's a good idea to generate from a small set of names so that you often generate the same name twice.
Yeah, I think that's definitely an interesting direction to explore. I'd be curious if we could find objectives that target that.
Cool. Thanks for the very cool talk. One thing you can do, that might be easier to do than manually tuning a distribution is writing your own unit tests, right? And that's in fact what programmers often do. And one other thing you can do with probabilistic programming languages is maximize the probability of some observed data. So I'm kind of curious whether you guys have thought about, or your system can handle the case where instead of manually giving a distribution, the developer writes a bunch of unit tests that might be sort of look like the distribution they expect test cases to come from, and then you optimize the generator to match that.
This is an interesting idea. I think we haven't considered it, but I guess you could imagine the tension here is that if you've already written those tests, you want to kind of extrapolate to find more interesting things. So maybe we could tune for them, but then add some kind of regularization parameter so we don't exactly generate those samples. There's some details on the paper here on how we can regularize weights. Definitely sounds interesting to try.
Cool, thanks.
Hey Ryan, thanks for the great talk. One thing that I was wondering is what happens if you provide an objective function that sort of fundamentally is unminimizable with respect to the generator template that you've been given, right? If I really ask for uniform distribution with the sort of 1, 2 weights, what happens?
Yeah, that's a good observation. So I guess when we choose numeric values for the weights of our generator, the generator structure itself limits the set of distributions that are even possible to a particular set. And the thing we do here is we have techniques to basically increase the tunability of generators so that you can inject dependencies into your weights so they can express a wider array of distributions. And there's more detail on that in the paper.
Awesome, thanks.
Thank you. The movement.